Hello and welcome everyone. We are so glad to have you join us virtually for this build session on building an end-to-end machine learning pipeline for big data. I'm Manoj and I'll be the moderator for this session. We have a dedicated area for you to ask questions and we request you to take advantage of it and keep the session really interactive. I'll bring up a bunch of questions for the presenters to address in the Q&A section towards the end of this session. Without taking any more time, let me invite Dennis and Megan to drive us through this session. Dennis and Megan, the floor is all yours.
Thank you, Manoj. Hello, and once again, welcome to this digital breakout session on building an end-to-end machine learning pipeline for big data. My name is Dennis, and together with Megan, I'll be guiding you through this content today. We are both program managers on the Azure Machine Learning team. When creating machine learning models, we rely on data, and often the volume of data is big. While more data could lead to training better models, big data has also introduced complexities ranging from having to maintain data lineage across multiple environments to dealing with various compute needs at each stage of development. Whereas for a small dataset size, say up to tens of gigabytes, you might find a single compute instance sufficient for both data prep and training. But as your dataset scales to a few hundreds of gigabytes or maybe a few terabytes, you might grasp the benefits of multi-node compute. But what beyond that point? For many teams, datasets might grow to such a size or a complexity that Apache Spark might be the most efficient way to prep your data. And then a typical pipeline might look as follows. One could use Spark compute, such as Azure Databricks, to handle ETL, run data wrangling for ML, explorative data analysis, and feature creation on either Spark or Azure Machine Learning multi-node compute. And as a last step, we might want to run training on optimized compute for the task. For instance, for deep learning, this might be on Azure Machine Learning Compute, in a multi-node manner on GPUs, and with a distributed backend for communication between the nodes. The specifics of this architecture might very well change dependent on your use case. By means of a demo, we'll look at a typical big data pipeline, covering various challenges brought by big data. And we are going to demonstrate how you can build up your machine learning pipeline using diverse compute types. You'll learn how you could use datasets across those pipeline steps. We'll show you how to keep track of assets as they're used in the various stages of the machine learning lifecycle. And lastly, we'll show you how to minimize the effort of deploying your models in production. Please send in your questions on chat, as we'll try to answer them during the second part of this session. Text classification is a common enterprise machine learning task that builds on the availability of lots of data. Think of document classification, intent classification for chatbot scenarios, or symptom detection and predictive maintenance. It would likely take little time to imagine similar use cases in your own organization. For this text classification demo, we'll use an open dataset of Reddit comments. Reddit is a content discussion and rating website where users can post, reply, and up or down vote comments as part of being in a community. And content on Reddit is grouped by a topic, such as movies or news, and those contain subcategories, also called subreddits. And based on a comment, we're going to predict which subreddit a comment belongs to. The pipeline that we review consists of 4 stages. A first step, where we capture new comments as they stream in from online, and where we'll process them into a clean format. A second step, where we sample some of the processed data to define multiple data sets that we take into experimentation. We then run a training. And lastly, we'll deploy and serve the created model as a web service to classify our comments. Now, let's break down each of these components.
To start, we'll look at a data engineering job that captures Reddit comments as they are posted online with a high velocity and volume. We make use of Spark's structured streaming capabilities to capture new comments, pre-process them, and persist them to storage for later analysis. Let's have a look at a notebook. First, we configure our connection to an Azure Event Hub, via which we capture the stream of Reddit comments. From the cell outputs, you can notice that data flows in with a binary format. We hence have to define a data schema and parse the content of the event message body with its correct data types, and we output the results in the table. For each of the comments, we capture multiple fields. We have the body of text containing the actual comment, a unique identifier for each, the subcategory, a category that organizes a comment, and these are the ones that we are interested in to predict later, the author, as well as a couple of statistics regarding the number of up and down votes a comment got from the community. Having structured the data and set the right data types, we save the processed data in partition Parquet columnar format to storage for better compression and performance while doing our later analysis. We'll now switch hats from the data engineer to the persona of a data scientist. Thanks to the data engineering activities, we now have a large set of comments available in storage for us to analyze. Before prototyping our model, we would like to get a better feel and understanding of the data, and hence we kick off with some explorative data analysis. First, we draw a random sample from a dataset to inspect the data quality. We also check for any null values, and luckily there are none. We explore how our data looks like when we would apply some normalization over the columns, and check how our top-level categories are distributed in this dataset. Now, instead of top-level categories, we would ideally be able to predict in a more granular level, and hence we select a subset of comments for one of those top-level categories and plot the subreddits that are in the sample. These seem a little less balanced than the top-level categories we saw before, but the sample seems large enough for us to take it into experimentation. Since the dataset is large, we will sample some data for the first iterations of our model. We define one dataset to only include a subset of the data. We'll use it for early experimentation so that we can be mindful of the compute resources that we use, and as well so that we can get faster feedback on our work. We also define a dataset based on the full data. As you can observe, we make use of Azure Machine Learning to define our datasets. We can easily do this on Databricks via the Azure Machine Learning Python package. As a last step, we version a dataset and do that for two reasons. First, to facilitate experiment reproducibility. Each time that we run an experiment, we refer a dataset by its version. And secondly, because of the abstraction that Azure ML provides us, by making it easy to mount and use the same dataset across multiple types of compute.
Let's shortly recap on our flow so far. We leverage Spark capabilities to prepare our data, and we then use Azure Machine Learning data sets to create multiple dataset versions right at the same place as where we explored our data. This helped us use only a relevant data sample in training to help us version our machine learning inputs and track them in experimentation, but also to work with our data in a more cost-effective way. And know that although we work with different tools, the platform allows us to let our data reside in one place on Azure Storage, but facilitate mounting across the various types of compute. Now that we have our data prepped, it's time to prototype our model. Megan will take over from here and walk you through.
Thanks, Dennis. To work with AML, we interact with an SDK, allowing us to work with an IDE of choice. I'm going to use VS Code because I like that it gives me good Git integration, code completion capabilities, and allows me to work with both scripts and notebooks. While experimenting, we often switch between various dataset versions, hyperparameters, and compute. Hence, we've got here a small helper script that gives us means to quickly adopt our training configurations. Let's walk through it. First, we're going to load our workspace. Then we're going to load our data sets that we made over in Databricks. We have both the full set and our subset. We're going to configure our training run by providing a training launcher script, a compute target, our input, and any environment details so that AML knows how to run our job. As we're in the early stages of our model prototyping, this is a simple configuration. You can always later extend this helper file with additional details. For example, we could let Azure ML help us manage and orchestrate hyperparameter search while passing the variations of hyperparameters to our script. Let's look at the script used to train our classification model. First, it takes a couple of arguments for configuring hyperparameters. Then we'll load our data set and convert it to a pandas format for easier data manipulation. Just as we're tracking our code and data versions, we are also tracking our experimentation results. In this example, we are using MLflow for tracking. We split our data run typical data prep steps for NLP types of problems, like counting word occurrences of our vocabulary and transforming our words using TF-IDF. We'll train our classifier and evaluate its performance on a test set. We'll calculate several performance metrics and log these with MLflow together with our model. Lastly, we're going to register our model in the Azure Machine Learning Model Registry. By logging our model to the registry, we enhance our lineage path, building a trace on our model version, what it was produced from which experiment run, providing a complete path till deployment. Azure ML's run history integrates with MLflow as an open source framework. Let's have a look at what was tracked in this run. Each run that is submitted on AML gets a unique ID to which metadata is logged. In this, we can see execution times, parameters, Git tracking, performance metrics, along with so much more. As we registered our model at the end of the run, we have a direct reference to our model registry. The model registry captures data and metadata associated with your model, including the experiment that was used for model training, all the artifacts that are packaged as a model. In this case, we logged our model according to the packaging convention used by MLflow, the data set that was used for training, and next to all of these, we also can find the list of endpoints where the model version was deployed to. In this case, we already made a deployment for the same model version to 3 geographical regions. Let's imagine at some point we find a data quality issue with our training data set. In such a case, these tracking details give us the knowledge to understand which models might have been impacted. Here's what's required to make a web service deployment. First, we're going to provide a name for our web service and specify the type of compute. Most importantly, we need a scoring file. This is where you'll supply the logic it takes to transform new data to a ready format for scoring, score the new data, and output the results. In addition to this, we're going to need to specify our models, what our model dependencies look like. For example, the list of pip packages that your model requires. A quick side note, you can also deploy from a deployment script instead of through the UI. Azure ML then helps us package and deploy our model with all the required dependencies, offering baked-in logging and monitoring capabilities, security controls, and also provides profiling capabilities to help you determine the right size of your container. We showed you how Azure ML helps us keep track of the code version, data version, and environment that we used as input to the experimentation. We also showed you that from the model registry, we can keep track of the experiment run that produced the model, where the model was used downstream, and the ML lifecycle deployment. Tracking this metadata is crucial for the operability of your ML solution. Let's recap what we've done so far. We streamed in data through Azure Event Hubs. We built an end-to-end pipeline that performed ETL and EDA in Azure Databricks. We defined multiple dataset versions to facilitate our experimentation process. We showed you model training in Azure ML. And finally, we ran you through the process of deployment. All while Azure ML's platform capabilities allowed us to keep track of our used assets, as well as make it easy for data to use data across compute types. If you'd like to learn more, we recommend you check out the following links. We've placed our example on GitHub, so you can play around with it yourself. Also, if you have any questions, please follow up with us in the live Q&A after the session or reach out to us directly. Also, I'd now like to thank our colleagues that helped make this presentation possible. In addition to all these live sessions, new on-demand content has also been posted. These are deeper dives into Azure ML services ranging from batch inferencing to AutoML. If you want to learn about any of these topics, please check out these sessions in addition to anything else you're attending during build. Thank you for listening so far. We're now going to switch over to the live Q&A, and we'll be back with you in just a moment.
Dennis and Megan, thank you so much for walking us through this wonderful demo. I understand that you are actually publishing the sample code for that was used in the demo on GitHub. I think it will be helpful if you can talk through the requirements and dependencies that are needed for doing this end-to-end demo.
Yeah. Great question. So you'll need an Azure ML workspace. You also need to spin up an Azure Databricks service. You'll have to have a storage account for your data. We had it in Blob, but also Azure Data Lake Gen 2 is a great option as well. You'll need a compute cluster or instance for training, like a GPU or CPU, which you can also create within the workspace. inference compute for deployment, such as Azure Compute Instance or Azure Kubernetes, which again can both be created in the workspace. Conda dependencies found in this repo, and nice to have would be some sort of IDE of choice. But again, we've also provided all this code for you.
Great, that's interesting. And I think in the demo today we covered like doing social media data set and creating a text classifier. Could you talk through one or two other examples and call out any key differences between them and what you covered in the session today?
Yeah, I can take that one. Like in the example that we showed today, it was really an example where we captured the scenario that related to streaming data, so high velocity, for example. And another type of scenario could be rather complex data or data that is, let's call it semi-structured. If I think of an example, one of them could be computer vision scenarios where you might have a lot of binary files like images and so. And at the same time, try to collect a lot of metadata or labels and so about these images. And you might be storing that metadata in like JSON files that are don't have a really specific structure. And you might want to search through that data to define a data set sample to take into specific training scenarios. So, for example, in the case of autonomous driving, that could be that you try to create a model to determine the light on a traffic light, and you might compose a data set that represents of data that is collected during the night, but also during the day, that is from various distances towards the traffic light and so. And you could then use Spark to query your metadata to come up with a file data set representing all the binary files to take into the specialist type of training. So in this case, the architecture would be pretty much the same, but there won't be the streaming component, but you would use the second notebook that we also showed today to help you sample your data. I hope that clarifies.
Great, absolutely. So let's switch gears a little bit, like thinking about a data scientist who doesn't have a lot of a data engineering background. How's all this stuff that you did around ETL in Databricks and maybe like all the stuff around deployment that you did after the model training? How hard is it for me as a data scientist without a data engineering background to accomplish?
Yeah, so I think for the ETL part, a lot of this depends on where your data currently is, what needs to be done to it, and your comfort level with that. For example, not all ETL will actually need Spark. You can actually just use, a lot of cases we found just using Azure Data Factory to pull in your data gets the job done. But again, this also depends on how much work is done. So if a lot of work is done, it might be very helpful to have a data engineer around, but for simpler cases, you can definitely do it on your own. And there's plenty of documentation to spin up on that. Training as a data scientist, that should be part of your job. So hopefully that part is doable. And then the deployment, I really want to touch on this. As a former data scientist, the deployment phase was always the part that I handed off to someone else to do, just because there was so much that went into it. And I have to say that this part is where there's really a standout for Azure ML, because it's very easy for you to deploy via the portal or through the SDK. It's super quick. No data engineering background really is needed, which is really great for if you especially want to be making fast prototypes, quickly deploying them to Azure Compute instances, seeing how they perform, scoring them. This is something you can quickly do. We have tons of guides and good examples up there. So I definitely want to make sure that the data scientists know that this end-to-end process they can actually do on their own.
Absolutely. Yeah.
Cool. So talking about deployment, you showed us how to deploy models, but could you build upon that further and talk about how could we do MLOps and what would be the next steps going from here?
Yeah, sure. I could take that one. I think like the demo that we showed today was really a sequence of steps like notebooks and initial like scripts that we run to prototype a model with, right? At some point, we might get to a point where we've proven the feasibility of this experiment that we try to solve, and we might want to roll in more and more dev and optimization practices there to make sure that we at some point can roll out a model while continuously validating its quality and then monitoring that as well. So I think that would consist of a couple of stages there. Like the first step would be like today we showed the notebooks as well as scripts. like to really operationalize this, like I'm a big like supporter of like really modular and well-tested code. So I would say that even for the streaming part, we got to refactor and develop that in a well-true way. Then we might stitch it all up in a machine learning pipeline. And how a machine learning pipeline can help us is to to execute all of these steps that we saw today in a sequence, in an automated or maybe in a scheduled way, so that we can operationalize the series of steps, but then like just as the complete graph. And the third step there would to get this to run across different environments. So many teams would work in a dev and a staging and a production environment. And using these DevOps practices, we can make sure that we develop a training pipeline first or a scoring pipeline first in dev, and then in a staged way are able to promote those across those environments. Now we have amazing integration there when you look from the product side between Azure DevOps and Azure Machine Learning that you should definitely check out, especially if you look at the integration there. You could, for example, kick off a deployment workflow based on the registration of a new model version, for example. So lots of interesting capabilities out there for you to explore.
Cool. Yeah, there's a lot of interest from the audience in trying out this, and it's awesome to see that the source is published to GitHub. Where did you source the data set from? Was it like available at some place to download, or did you go scrape it using a web scroller or something like that?
So this is actually, it's an open data set of Reddit, but part of it is that we also showed that streaming in new data as well. So a mixed answer to both of those. But yes, the data set's also publicly available.
Got it. Cool. How did you break the data set into like two different data sets, and like, could you comment on that?
Yeah, so I can comment on that. Like in the first notebook, what you saw as one of the last steps is that we've written our output, like a processed output, to a process table in Spark, which is residing on storage as a backend. And what we did as part of that operation is that we partitioned all the new comments that we got in by subcategory, by this subreddit. So each of them would get their different folders. And for the sake of this example, we specifically want to version across different subreddits. So we defined a dataset version over the Parquet files that would be in across the folders for which we would want it to combine as a dataset version. And that is the way that we run it. There would be one approach. If you face it and you go deeper into your experimentation, you may want to sample more thoroughly, and write intermediate results maybe to a separate place where you can define a dataset version over it. But that would be just another approach that you could use. Yeah.
Interesting. Today you showed us a demo using Azure Databricks, right? Like we also have this cool new Spark stuff in Synapse. Could you talk through how similar or how different would it be if I were to use Synapse instead of Databricks?
Dennis, do you want to take that one?
Yeah, sure.
Okay.
Yeah, indeed. So we got some exciting new capabilities there with Spark support in Synapse. Like the way of working here is actually very much the same as what we saw today in this demo. So with either Spark compute that you might be working with, so that might be on Azure Databricks, that might be with Synapse, but it might also be with HD Insight. You would handle your data prep and write it on Spark, then route it to storage, and it might be Azure Storage as well as Azure Data Lake Store, Gen 1 or Gen 2, for example. And using that process data, we would use an Azure Machine Learning data set to load that data back in from Azure Machine Learning. So that would be the same way of working as what we saw today, but just with a different flavor of Spark and dependent on what you prefer to work with.
Do you want to call out that Synapse with Spark was actually announced for open preview at Build, so definitely go check that out if that's something you're more interested in.
Yeah.
Cool. Yep. So we have heard of this automated machine learning capability. That's one of the highlights of using Azure Machine Learning. How could I have leveraged AutoML in this scenario?
Yeah, so AutoML is pretty cool, in which case, for a lot of, especially the deployment stuff we showed, it takes care of that for you. What you'll typically see in an AutoML pipeline is you might be loading in your data through Azure Data Factory, and then AutoML actually takes care of some of the data prep for you, which is really cool. Training's also taken care of for you. And then for deployment, all you really need is a name and description, compute type. AutoML takes care of that scoring file we told you about and the dependencies. And so it really is this like idea of a one-click deployment. So it's even faster than what we showed you here. There's also another live session which actually walks through AutoML and different training cases for machine learning, more of a machine learning modeling focused talk than this one was. So you should definitely check that out if you're interested. But yeah, some of the key differences here is that it just takes care of a lot of the steps we already showed you for you.
Great. That's great to hear, right? One of the things we saw toward the end of the demo was like when we are doing the training, we are like leveraging MLflow to log a lot of our training metrics. That seemed pretty cool, right? And this is Azure MLflow is like an open source component. Could you talk through more about that? Like, how does MLflow work with Azure ML, and like how is it so seamless to use OSS stuff with Azure ML?
Yeah, so what we showed you today is, in fact, the integration of Azure Machine Learning's run history capabilities with MLflow tracking. So with MLflow, we can log and capture certain metrics and values, plots, and like that we might collect from a training run. And Azure Machine Learning's run history provides you with the tools to compare those metrics across the runs, visualize them, and have that logging really enables you to reproduce results and look back over time. So that is the integration there that you'll find.
Yeah, I'm gonna really engage you more with the standards the customers really want to use, which case was MLflow. So we really wanted to integrate in so they can log using the syntax they prefer to see their results, and all of it's still being stored within the ML workspace.
Great. I think we have probably time left for one or two more questions. So let's take this one. Today, like, when we deployed the model, we deployed it to an endpoint, and we could like do real-time scoring with that deployment. How different would it be if I had to do batch scoring kind of scenario?
Yeah, I could take that one. And it brings us back again to the machine learning pipelines that I called out before. We got in, like those pipelines help us take data from specific places on storage, for example, and then execute a couple of transformations over there. We got different pipeline steps that you could use. And one of the new steps that we introduced is the parallel run step, which helps you to point to a specific data set. And then the step will help you to distribute the task that it runs on each chunk of data across different nodes. Enabling you, in fact, to do inferencing at a larger scale. You would put it in a pipeline and then publish that. And the cool thing with ML pipelines is that as soon as you publish it, the pipeline gets available as a REST endpoint. So it's very easy to integrate with different types of systems. Now, if you would like to learn more about this parallel run step, there is an on-demand session from Tracy who will do a more deep dive into that. It was listed on one of the slides that we had right before.
Great. So we are almost end of time, and let's take one last question. We have been hearing of this cool new stuff called Dask as an alternative for doing data prep. Are there any plans, or how could I kind of leverage Dask today with this Azure ML system?
Yeah, so Dask is an open source framework that helps you to run specific like data prep or training steps in parallel across different nodes, for example, on Azure Machine Learning Compute. It's an open source project. And like one of our PMs wrote a tutorial on how you could use it today in Azure Machine Learning. So that's a blog by Daniel Snyder, and maybe one of the traffic controllers is able to put it on the chat, and otherwise I'll make sure that that link lands to you as well later on.
Yeah, and to quickly add
Awesome.
in, so you saw us use Joblib within our demo for single machine parallelism. You could substitute in Dask there within our demo.
Brilliant. We are pretty much out of time for today's session. Thank you so much, Megan and Dennis, for walking us through this. We hope all of you enjoyed this session and found something useful to take away from here. Keep connected, keep exploring all of the fantastic tools that are available